In dive bombing, we correct the aim in range by pulling or pushing the stick, just as we do in horizontal flight. This raises or lowers the line of flight to the proper point of aim in range. It is harder to correct for range in a shallow dive than in a steep dive, because the same error in estimating dive angle makes a larger error in range. On the other hand, it's easy to correct for range in a steep dive because the same amount of error makes a much smaller error in range than in a shallow dive. Furthermore, the same amount of error in estimating our release altitude will cause a greater range error in a shallow dive than in a steep dive. In a shallow dive, the bomb falls much farther from our point of aim than it does in a steep dive. Estimating this range correction introduces an error. We have only the size of the target to help us estimate our corrections. In making large corrections, this leads to error. It is also much harder to estimate the dive angle of a shallow dive correctly so that our expected error is still greater. Let's make a dive on a windless day. If we reach release altitude at a normal dive angle with our line of sight on the target, the bomb will hit the target. Gravity causes the bomb to land short of the line of flight. The sight is bore-sighted, so the line of sight is below the line of flight. If this is done, the bomb will hit our point of aim when we release in a normal dive. If, however, we're diving the airplane toward the target and find that we're too shallow, we must change our line of flight or the bomb will fall short of the target. Of course, on nearing release altitude, we can pull up the nose, raising our line of flight. This corrects our bomb toward the target. But it does not change our vertical angle with respect to the target. As we change the line of flight almost instantly when we pull up the nose. This correction changes the bomb's path because the bomb is affected by the airplane motion which is along the line of flight. The bomb lands far short of our line of flight and the line of sight because of the large effect of gravity in a shallow dive. The range correction is so large that it cannot be estimated accurately. Let's see what happens if we steepen the same dive to the normal dive angle as soon as we see we're too shallow. Now, although the bomb will land on the line of sight, it is far short of the target. As before, we can pull up the nose, raising our line of flight and line of sight over the target to correct for range. But now our vertical angle from the target is even less than before. And our range correction is still larger. We are worse off than we were to begin with. Let's repeat the same dive and try to correct it once more. This time, we'll pull the nose up whenever we see we're too shallow. If we release our bomb with no correction, it would land even further short of both the line of flight and line of sight than it did in our original dive. But by diving shallower, we have raised our line of flight far over the target, so that the bomb will land over the target even though it's further short of the line of sight. However, our vertical angle from the target is now correct, and as we near release altitude, we correct our line of flight by pushing the nose over and putting our point of aim on the target. This correction puts us in a normal dive so that the bomb will land on the point of aim. So, If we start a dive incorrectly, we can still release in a normal dive. If we find ourselves in a dive that's too shallow, we should raise the nose, steepening the vertical angle from the target in order to reach release altitude near the normal dive angle. The bomb will land so near the point of aim that range correction is easy to estimate. On the other hand, if we find ourselves in a dive that's too steep, we should push the nose over to correct the vertical angle from the target and again reach release altitude so that when we make our range correction, we are in a normal dive. Now that we've considered the problems of range, let's consider the problem of deflection. We must keep the bomb from falling to either side of the target, as seen by the pilot. We correct for deflection by turning the airplane right or left toward the target, because we must correct the line of flight of the airplane. Assume that the airplane is in a shallow dive. A small amount of turn will correct a large error in deflection. Now let's aim the airplane at the ground in a steep dive. We see that to make even a small correction in deflection, the airplane must be rotated almost 90 degrees. Turning an airplane in a steep dive is difficult. If we apply much rudder in a steep dive, the airplane skids instead of turning. A skid like this may skid the airplane just enough to point the line of sight directly on the point of aim. Because we can hold the line of sight on the point of aim, we get the false impression that the airplane is diving toward the point of aim. This is an illusion, because even the heaviest skid gives the airplane very little horizontal motion in a dive. Because of this, it's important for us to remember that in a steep dive, we turn the airplane with much more aileron than rudder, like this. We have seen that it's easier to correct for range in a steep dive and for deflection in a shallow dive. We can't do both at the same time. The only thing we can do is compromise and make our dive somewhere between the steep and the shallow dive. Such a compromised dive is called the normal dive, in which we release our bomb in a dive angle of about 65 degrees. The normal dive starts shallow enough so that deflection can be corrected with a relatively small turn. The normal dive angle ends steeply enough so that corrections for range are easily estimated. Experience has shown that a dive near this angle is best for bombing targets when we have to concentrate on both range and deflection. There are some targets, however, such as bridges, on which we can concentrate on one aim factor